Now in this class we will talk about the formulation of a beam column element. Now we will consider the axial deformation together with the bending deformation and come up with the new stiffness matrix for the beam element. Now in order to do that, let's take a simply supported beam. And let's assume that we have some loading on it. And because of this loading, we will see that the beam will bend as follows. So that's the deformed shape. And let's say that that's the x-axis and that's the y-axis. Now, for this bending problem, we know that the strain energy is equal to the curvature multiplied by the moment, and you integrate it over the length. So let's write it. So for this given bending problem, the energy due to bending will be is equal to 1 over 2 EI d square V dx square dx, where V represents the transverse displacement. Now in all our formulation, the beam element formulation, we said that the length of the beam is equal to the length of the deformed beam. So we just assume that the deformations are small, and we say that these two lengths are equal to each other. Now for this formulation, let's not assume the length of the beam of the deformed beam is equal to the original length. Remember that this is our main assumption when we talked about the bending deformation. So here we are not assuming that anymore, okay? So, thus, for an infinitesimal element, and here we are also ignoring the shear deformations, I can write the following relationships. So I have this infinitesimal element whose length is dx. Now it bends, so when I take a look at the infinitesimal element, this is what I see. And the length of this is equal to ds. And we know that this angle, since I ignore the shear deformations, this angle is equal to dv over dx. Now in that case, this length will be equal to dv over dx multiplied by dx. Now if you calculate the length of this, ds will be equal to square root dx squared plus dv over dx squared multiplied by dx squared. So that's the length of the deformed shape for an infinitesimal element. So I can just simplify this as dx in parentheses 1 plus dv over dx square. Now remember that we were ignoring this part. In our previous bending deformations definitions, we were saying that ds is equal to dx. Now we say that, okay, I'm no longer ignore this part. Now again, I have square roots here, which I don't like. So instead of using the squares, I using Taylor series expansion. And ignoring higher order terms. I can write that ds is equal to 1 plus 1 over 2 dv over dx squared multiplied by dx. So here we are also making an approximation. I'm ignoring the higher order terms now. Now let's continue. I need a strain definition. So I'm ignoring small deformations. Then if we use engineering strain definition, for axial deformation, due to bending. Remember that here I consider the length change. So if there's a length change, then you can say that there's an axial deformation. So let's represent that strain as EM, the membrane deformation, is equal to ds over dx gives me the amount of length change divided by the initial length, which is equal to dx. So that's ds over dx minus 1. That's equal to 1 plus 1 over 2 dv over dx squared minus 1. These two cancel, and at the end of the day I obtain my membrane strain as equal to 1 over 2 dv over dx squared. And actually this strain definition is nothing but the Green's strain. Okay, so with this assumption, with this approximation, and using the engineering strain definition, I end up with the Green's strain. Okay, so here this is the membrane strain. If there is no loading, no axial load on the system, then there is no additional work done due to bending by the axial load. Let's see what happens if there is an axial load. Now in that case, I'm saying that, okay, I'm adding an axial load here. And let this axial load be equal to P. Now in that case, if there's an axial load on the member, there will be additional strain energy for bending. So here I'm not calculating the total strain energy due to the axial load. I'm just calculating here, just writing the additional strain energy for bending deformation. And in that case, that additional strain energy, let's write it this way, Um is equal to, from 0 to L, P times the membrane strain integrated over the length of the member. And if we put the membrane, the green strain definition into that equation, we have the following: 1 over 2 from 0 to L, P times dV over dx squared dx. So the total energy due to bending deformation will be equal to, U is equal to 1 over 2 from 0 to L EI d square V dx squared plus 1 over 2 from 0 to L P times dV over dx squared dx. Now we have an additional term here, okay? This is the additional term, and this additional term is because of the considering the length change due to bending deformation. Now we know how to obtain the stiffness matrix for this part of the equation. Now I want to focus on this part because we know that this will give me another stiffness matrix. So let's take a look at that. Let's do the finite element formulation. Now remember that we come up with the following displacement interpolation for the beam elements. So V is equal to, I is equal to 1 to 4 Ni Vi. And in that Vi is equal to theta I Vj theta j. And in that formulation, N is the Hermitian shape functions. Now, if we focus on the membrane energy, due to bending deformation, we have the following: Um is equal to, from 0 to L, P times, I have 1 over 2 here, P times dV over dx squared dx. And if we put that interpolation into this one, we have the following: this is equal to 1 over 2 from 0 to L dni dx times Vi transpose multiplied by P multiplied by again dni dx Vi integrated over the length of the member. Now we know this form, so if I just say let G matrix is equal to dni over dx, then my stiffness matrix will be equal to, let's call this one K sigma is equal to, from 0 to L, G transpose multiplied by G times P times dx. This stiffness matrix is called initial stress or geometric stiffness matrix. And when you evaluate that matrix, we end up with the following. I have P over 30L here, 36, 3L minus 36, 3L, 4L squared minus 3L minus L squared in 36 minus 3L and 4L squared. And that will be another symmetrical matrix. So in that formulation, the only thing that I did is consider the length change due to bending deformation. So this gave me an additional membrane energy as follows. And by using that and the finite element interpolation, I calculated a new initial stress matrix. Now let's obtain the initial stress or the geometric stiffness matrix for the beam column element. Now we just gave the result, but let's see how we obtain it. Now we have the Hermitian polynomials. These are defined in the natural coordinate system. Now in the geometric stiffness matrix, we only need their first derivatives. So here I'm calculating their first derivatives, and we will need to evaluate the G matrix. Now this is the G matrix. Now I need this to convert the natural coordinate system to the coordinates of the beam. So at the end of the day, when you put the derivatives into G matrix, this is what we have. That's the G matrix, okay? So I'm evaluating that from -1 to 1 and multiplied it with L over 2. And at the end of the day, I have P G transpose times G here. So when you symbolically evaluate that integral, we have the following result, but I want to write it in a much simpler form, so I'm dividing it by P over 30L, and when I do that, I obtain the same stiffness matrix. That's the geometric stiffness matrix. So the matrix that will define the bending deformation, considering the length change, we have two matrices. One of them is EK linear. This is the classical stiffness matrix that we have been using, plus P times, or let's write it this way, K sigma, the geometric stiffness matrix, and I have K linear plus P times 30L and then the rest of the coefficients. So what's important here is when P is plus, or it means that it's in tension, then these coefficients will increase the stiffness, for bending. Okay, so when P is negative, as you can guess, it will reduce the stiffness. It will make your beam more flexible. And of course, since I'm subtracting the geometric stiffness matrix from the linear stiffness matrix, this subtraction may give me zero stiffness, right? And sometimes even negative stiffness, which actually means that we have buckling in the system. So this is the final stiffness matrix that describes the bending behavior. And remember that the only assumption that we make to obtain the stiffness matrix is we consider the length change. So we only use the green strain definition. So we are saying that in this element, the displacements, the rotations are small. They are still small. The deformations are small. So the only assumption that we remove from the linear stiffness matrix derivation is the length change due to bending deformation. And at the end of the day, we obtain the following matrix. So as you see, the K matrix depend on P. So as you perform the analysis, P will be your internal force. So it changes at the deformations change. So that's where the nonlinearity comes. And we will see how we can perform the buckling analysis and a nonlinear static analysis for a beam column element like this. Let's very briefly see how we can obtain the geometric stiffness matrix for shell elements. So I will use the same assumption as I did for the beam column element. Geometric stiffness matrix for shell elements. Now we see that when you consider the length change due to bending deformation, we end up with the green strain definition. So we'll start our formulation with the green strain. Remember that the green strain is equal to 1/2 final length squared divided minus the initial length squared divided by the initial length squared. So if we apply this green strain to 3D deformation, we have the following: Gx is equal to del u over del x. Remember that this is the linear strain, plus we have the higher order strain. That's del u over del x squared plus del v over del x squared plus del w over del x squared. Now the green strain y will be equal to del v over del y plus 1/2 del u over del y squared plus del v over del y squared plus del w over del y squared. Okay, so you can write the strain in the z direction, same form. Now the shear strain gamma xy will be equal to del u over del y plus del v over del x plus I have del u over del x multiplied by del u over del y plus del v over del x multiplied by del v over del y plus del w over del x multiplied by del w over del y. Okay, now remember that in a membrane element we have the following membrane forces. So let's remember that. That's the membrane element. So here I have Fxx, here I have Fyy, and I got the shear forces Fxy. Now the strains, now here we are talking about the axial strains. When there is a transverse displacement, here I'm just considering the nonlinearity due to the transverse displacement W. So I'm just taking a look at only these terms, okay, the same formulation as I used in the beam element. Now in that case, the green strain is equal to 1 over 2 del W over del X squared. Now the green strain in Y direction will be 1 over 2 del W over del Y squared, and then the green strain for shear will be del W over del X times del W over del Y. So these are the membrane strains due to bending deformations, and these are the corresponding membrane forces. So the strain energy or let's call it the additional strain energy due to bending deformation will be as follows. So let's use the same. UM will be equal to, now I'm integrated thing over the area, 1 over 2, the force is Fxx, so instead of P we have Fxx here, and del W over del X squared plus 1 over 2 Fyy multiplied by del W over del Y squared plus the shear force Fxy multiplied by del V over del X times del W over del Y. And you have to integrate this over the area. Let's call this one equation star. So if I reorganize that equation, and writing it in matrix form, I have the following. UM is equal to 1 over 2 double integral del W over del X del W over del Y transpose. I have Fxx, Fxy, Fxy and Fyy here. Del W over del X, del W over del Y integrated over the area. And this is the additional strain energy due to bending deformation. Now let's do the finite element formulation. Now I'll do it for the quadrilateral element, quadrilateral thick plate element. So I will use its shape functions. With bilinear shape functions. Now W, remember that we were using the bilinear shape functions. I is equal to 1 to 4 and I, Wi. This is the transverse displacement interpolation. Now, in that case, the additional strain energy will be equal to 1 over 2. I have double integral here. Vi transpose del Ni del X del Ni del Y transpose multiplied by the stress matrix or the internal force matrix Fxx, Fxy, we have Fyy here, multiplied by del Ni del X del Ni del Y, okay, dA. So if I call this vector as the G, let's call this one as our stress matrix, and this is also G. And from the energy formulation, we know that the initial stress matrix for this thick plate element will be equal to double integral G transpose times stress matrix times G integrated over the full area. And in that case, G will be equal to del N1 del X del N2 del X and at the bottom I have del Y del N2 del Y del N3 del Y and del N4 del Y, where Vi is equal to the transverse displacements at the nodes. So you calculate the G matrix, perform this integration, and you obtain your additional strain matrix. And you can add it to the stiffness matrix that you obtain for the shell element. Of course, we are just adding this to the plate bending part of the shell element. Remember that this is of course for the flat shell elements. We are assuming that there is no additional coupling between the axial forces and the plate bending behavior. Our element is not curved, and with these assumptions we calculate the initial stress matrix and add this initial stress matrix to the corresponding places for W1, W2, W3 and W4 in the stiffness matrix.